Today, we're going to pull back the curtain on large language models. And you know what's wild? This whole journey, it starts with a simple little equation you definitely learned in high school. And it ends with these thinking machines that are changing just about everything.
But hold on, this whole thing kind of hangs on one giant question, right? Computers are just fancy calculators. They're all about numbers. So how in the world can a machine that only gets ones and zeros ever understand something as messy, as beautiful as human language? That is the puzzle we are going to solve together today.
So here's our game plan. We're going to start with one tiny, simple building block. Then we'll figure out how to turn words into numbers and give our machine a memory. After that, oh man, we get to the revolution that changed everything. We'll see why large is the absolute magic word, and finally, we'll add that crucial human touch that makes these things actually useful.
Okay, so where does this all begin? Believe it or not, to understand an AI with billions and billions of parts, we first have to understand just one thing: a simple, straight line.
Yep, this equation right here. It's the very first Lego brick of our entire AI. You probably remember it as y equals mx plus b from math class. It's the exact same idea. W is the weight, that's what sets the slope, and b is the bias, which just moves the line up and down. It seems almost too basic, right? But I promise you, every gigantic AI model out there, deep down, is just a ridiculously massive structure built from simple ideas just like this one.
So how does a simple line learn anything? Well, it follows this little four-step dance. First, you feed it a ton of data. Second, you give it its structure, in this case, our simple line. Third, you give it a way to grade itself, to measure its own mistakes. We call that a loss function. And finally, you just start tweaking those W and B knobs again and again and again, trying to get that error as low as possible. That four-step loop, that's the heartbeat of all machine learning.
All right, so our model can learn from numbers. That's great, but language isn't numbers, it's words. And that brings us to our first huge problem. How do you translate something as rich and full of meaning as a word into a number a machine can actually process?
So the first attempt was, well, it was pretty clumsy. It was called Bag of Words, and it basically just counted words up, totally ignoring their order. So a sentence like, "the cat chased the dog," would look exactly the same as "the dog chased the cat." I mean, come on, all the meaning just vanishes. The real breakthrough is this idea called word embeddings. Instead of counting, we represent words as coordinates on a huge, multidimensional map of meaning. And on this map, words that mean similar things get placed close to each other.
And here's where it gets kind of mind-blowing. Researchers found you could do math with these words. If you take the map coordinate for king, you subtract the coordinate for man, and you add the coordinate for woman, you land almost exactly on the coordinate for queen. This was huge. It meant these embeddings weren't just storing definitions, they were capturing the actual relationships between concepts.
Okay, so our model gets words now. Fantastic. But sentences aren't just a jumble of words, right? They have an order, a flow, a story. The model still can't tell that story because it has no memory of what came before. It needs to understand context.
The first real solution to this was the recurrent neural network, or RNN. And the genius of the RNN is that it works in a loop. As it reads each word, it doesn't just look at it and forget it. No, it keeps this little hidden state. You can think of it like a running memory that it passes along to the very next word. For the first time, a model could actually remember the beginning of a sentence by the time it got to the end.
But RNNs had a fatal flaw. Their memory was really short. You know, in a long paragraph, that memory of the first sentence would just fade away by the time it reached the last one. This technical issue, the vanishing gradient problem, basically meant that crucial context was still getting lost in the noise. To solve this memory problem, we needed more than just an improvement. We needed a revolution.
And in 2017, that revolution arrived. It was called the transformer. And this new design didn't just tweak the RNN's memory, it threw the entire rulebook out the window. This is the architecture. It's what powers every single modern LLM you've ever used.
Its secret weapon is a brilliant idea called self-attention. Remember how the RNN had to read one word at a time in a line?
The transformer looks at the entire sentence all at once. For any word it's looking at, it can directly connect to and weigh the importance of every other word, no matter how far away it is. It's not walking down the street anymore. It has this bird's-eye view of the whole city.
So how does this bird's-eye view work? Okay, let's use an analogy. For every single word, the model creates three things. A query, which is like a little reporter asking, hey, who in this sentence is actually relevant to me? Then there's a key, which is like a name tag on every other word, saying, hey, this is what I'm about. And finally, a value, which is the actual meaning, the real substance of that word. The reporter, the query, looks at all the name tags, all the keys, to find the most relevant ones. It then pays more attention to their information, their values, to figure out what it should mean in this context. It's this elegant little dance that lets every word understand its place in the whole sentence.
So, the transformer architecture was the revolutionary recipe. But a great recipe needs ingredients, and in our case, it needs a truly massive amount of them. This is the second half of the story, scale. It's what puts the large in large language models. 70 billion. That's how many parameters, or you can think of them as tunable knobs, are inside a model like Llama 3 170B. Every single one of those 70 billion knobs holds a tiny, tiny piece of information it's learned about grammar or facts or just the patterns of how we talk. It's this absolutely mind-boggling number that gives the model its power to know so much. And to really put that scale into perspective, just look at this. The little toy model we've been building in our heads might have, say, 2 processing blocks and a meaning map of 128 dimensions. Llama 3.1 has 80 blocks and a map with over 8,000 dimensions. We're not just in a different league here, we're playing a completely different sport.
And this enormous scale, it led to a total shocker. I mean, not that long ago, the expert opinion was basically what you see here, that it was pointless to think a machine could really get language just from text. It needed to see and hear and touch the world. But it turns out that was wrong. If you just make the model big enough and feed it enough text, something that looks an awful lot like understanding just emerges, all from predicting the next word.
So now we have it, this incredibly powerful, massively scaled up transformer. But on its own, it's still just a raw prediction engine. To turn this incredible technology into a helpful, and more importantly, a safe tool, it needs one final critical ingredient: the human touch.
Just look at the difference this makes. A raw, pre-trained model is basically a super smart parrot. It only knows how to predict the next word. If you ask it to continue a list, it might just start rambling about what lists are. But after fine-tuning, after training it on a smaller, curated dataset of what humans actually want, it learns to follow instructions. It gets the intent behind the words.
That human touch is also about making these models more reliable. A really cool technique for this is called Retrieval Augmented Generation, or RAG. It's a super simple but powerful idea. Before the LLM even tries to answer your question, the system first goes and looks up relevant facts from a source you trust. Then, it literally sticks those facts into your prompt, basically giving the model cheat notes and saying, hey, answer the question, but only use these facts I just gave you. It's a great way to cut down on made-up answers.
And all this leads to some really important challenges that we just have to keep in our heads. These models can hallucinate. They can state things that are completely false with total confidence. They soak up all the patterns from their training data, and that includes our own biases. Training on the entire internet, well, that brings up some thorny copyright questions. And maybe most importantly, their inner workings are still pretty much a black box that we don't fully understand.
So there you have it. We went all the way from a single line in a high school math book to a machine that can process the incredible richness of human language. And that leaves us with one final, huge question to think about. We've taught machines to understand our words. What happens next, now that we're teaching them to see our world? Because that next frontier, it's already here.